Hello, everyone, and thank you for coming to high-speed query acceleration with execution with accelerators and C++. Few words about me. I'm Dathskovsky. I have more than 16 years of developing with C++ and system development. I'm working in a great startup company that's called Speedata. We are developing the next big thing in big data. We are developing an accelerator, which is general purpose computing and accelerating big data. So if you are using queries, you have something to wait for. I'm also on LinkedIn. I have weekly C++ postings. Sometimes those are riddles, sometimes those are new things in C++. So if you would like, please follow me. Now, this is the agenda for us today. Why do we actually need to accelerate queries for analytics? We will talk about computer architecture. We will talk about the history of computers and how they were developed. We will see how does our MFC or APU fits in with all those architectures and what is so special about what we are doing. The second part of this will be how to code those things. As you may think already, those are massively parallel computings, and they're really, really hard to program. So how are we helping our users to program your C++ code, to program your queries to be much, much faster? We will see some code examples for simple queries, and then we will see how we scale out to much more complex queries, and we're still able to compile them and process them. Before we start, we need to understand, I already said a couple of words that maybe no one understood. For example, APU. APU is an analytic processing unit. Our old CPU is called APU. Inside this APU chip, we will have MFC, which is the multi-flow core. This is the general purpose computing core, and we will be talking about this talk. Now, why do we need query acceleration? As big data becomes bigger and bigger with years, everyone's using the internet here. All the companies like Google, Facebook, they're all using big data to query about what kind of things you like and what to show you, what kind of movies you would like best. That's for Netflix. And so processing it becomes more and more dependent on computing. For example, we have some users that their computation takes days on multiple servers. And this is something that makes them not run their queries or run them just once a month instead of running it every day as they want. The second thing that we need to look at is the energy consumption. If we need to run queries faster, we need more servers. For more servers, there will be more CPUs. More CPUs will consume more energy, and then you will need to cool these things down. So you need a cooling system that will cool all those servers down, and that's more energy. So it's energy and energy. And at the end of the day, the cost. So if you have more data to process, you're using more servers, you're using more energy, and that means there's more expenses. So with Speedata, we will be greener. You will be able to do the same thing as with many servers, just with one server, and we will be much faster as well. So let's start with the history of computing architecture. We need to understand how we got to what we are doing here. At the beginning, there was this. Who knows from where this image came from? Someone recognizes it? 2001, that's right. Funny story about 2001. The name of the computer was HAL. It's a wordplay for IBM. So if you will take I minus minus, B minus minus, and M minus minus, you will get HAL. So they were very afraid from IBM computing back then. Let's start with the first thing that was created for CPUs, von Neumann architecture. Von Neumann architecture was created in 1940s, and it's the basic machine that is still used until today. Still x86 and the ARM processor, they're still using the same principle of von Neumann. So the principle is that we have a processing unit with arithmetic and logical unit and registers. We have a control unit with program counter. We have memory that we need to access. And we have external mass storage. Plus, we need the I/O to that. From that concept, we have created something that's called CPU. CPU is executing instructions sequentially. A sequence of instruction is called a program. For example, here we have 3 instructions that will be executed one after another, sequentially, and that's a program. This is a simple CPU diagram where we can see how we took von Neumann and created something a little bit more complex from it for the first time. So you can still see it's basically the same von Neumann architecture. You have inputs, you have outputs, you have control units, registers, you have logic units, and you have main memory. Here I'm representing black lines is the data that is flowing through all the mechanism here. And you have the red lines, those are the controls. So controls, each and every one of those units may signal the other one to say what it's supposed to do. There are different types of CPUs that we are using daily. So the first type that I want to show you is the RISC CPU. RISC CPU is a reduced instruction set. Basically, it means that all the instructions have the same size, for example, 32 bits. And those instructions are usually very, very simple. So you have add, you have shift left, you have mul. You don't have anything that is too complex. And to illustrate that, I'm using the same program that we saw before. Instructions, they're on the same size, and they're executing one after another. The second one that I want to talk about is CISC. CISC is complex instruction set computing. It has variable length of instruction, and it has very complex instructions and not complex instructions at all. So for example, on x86, you have load, add, store in one instruction. And for this, I have illustrated that we have one instruction that is really big and one instruction that is really small. Now, with time, computing became more popular and we had to do computing that is more complex. So please be faster. The first and maybe the most important thing that was added to CPUs was the pipelining mechanism. Instead of running the instructions sequentially, we are doing it in a pipe. So the first instruction, we are fetching it. After we fetch the instruction, we can already go and fetch another instruction because the first instruction is already in the decode stage, and so forth and so on. But even with that, we have a problem because if instructions will take more time, for example, in execution, if you have a memory access, that will take more time, and so instructions that are coming after it will have to stall. If we have data dependencies, instructions will have to stall. So basically, those instructions that are stalling, they're injecting NOPs into the processor, and NOPs is nothing. We are just losing cycles. The second, and again, a very, very important optimization that was added to CPUs is the branch predictor. Here I wanted to show the simplest branch prediction with 2 bits that is actually used. And what you can see here is basically telling the CPU is looking at the history of the branch and is saying, okay, is it strongly taken? Is it strongly not taken? And each time it's taken, it considers it to be strongly being more and more predictable to be taken. What it does, if we already took what it does in the end is just saying, okay, if it's strongly taken, so I might presume that we will do that branch anyway. So I will take and compute it. I will not wait for the branch to be calculated or to be executed. I will just do it. Another problem with that is that if it's wrong and it's dropped, then we will just have to flush everything and we lost a lot of cycles. But for loops, and if we have ifs inside the loop, usually they will be taken and we will save a lot of time. The next optimization is a very important optimization, but it's more complex than the other ones that I already showed you today. It's the out-of-order execution. So as I mentioned before, instruction may stall. just because one instruction is taking longer than the other, or if we have some data dependencies. Here with out-of-order execution, you don't need to wait. So as you see here, basically add and sub, they are not dependent on each other, and they are not dependent on the move instruction that takes something from the memory. So they can be reordered, they can be done in the same time without the stalling. Out-of-order computing is hard. It's a hard thing to do, and here you see one of the options how to implement this computing. So here we always start with something that is in order. We have the fetch and decode. We have the branch predictor that we saw before. Afterwards, we are going to something that's called a reservation station, and that's basically is the reordering. It will reorder, it will change name of the registers, and it will make it more possible for the processor to compute those at once. Afterwards, it goes to the issue queue. The issue queue here, you have an example of a processor that have more than one execution unit. After that, it goes to the reorder buffer, where we need to reorder the instructions that we got, the answers that we got from the instructions, and then commit it in the same process as if it was in order. Even that wasn't enough. We still had some stalling, and it still made things better, but we need more computing power. We need to make things faster, and that's why SIMD was created. SIMD, or vector computing, vectorization computing. For example, in Intel, you have AVX 512 in their Xeon CPUs. Those are vector machines. You can do the same instruction on multiple data. So basically, we can take the same instruction and work on a lot of data in the same time. But even that is not enough. And that's where GPUs getting much, much better. But they're only better sometimes. So GPUs, they're only good when you have non-dependent data. That means they can work, all the threads can work at once at all the data without interfering with each other. If you have something that is dependent or structured data, that will not work. But basically, GPGPUs made the world different. They accelerated programs. They created something that's called a single instruction, multiple threads, not single instruction, multiple data. And that's basically because we're giving the same instruction to a huge amount of threads, and they will process the data. Here we have a simple diagram of a GPU. It's almost the same as the CPU because, again, this is a von Neumann machine that was reduced to something really small without branch predictions and all those special out-of-order units. But we just have a lot of CPUs in the same machine. This is a picture of GH100. This is the latest GPU from NVIDIA. It has 144 SMs. SM is a streaming unit. It's their basic CPU. It's called SM. Each SM has 2,000 threads in it. So you can imagine how many threads this thing can run. Here we see an example of the architecture of GPUs, how it works with the system. So if you are working with a GPU, you always need a CPU as a host. The CPU communicates with the GPU via memory. So we have DMA, the host memory, the host itself is copying data from itself to the GPU memory. Then we have contacts pages and channels because a GPU is a streaming machine. So we can stream a couple of different programs to the same time to the GPU, and it will do it by a different channel. Afterwards, all the instructions are going to the computation cores, and those computation cores are basically the one that execute the kernels that we know, and they run them. Afterwards, if you want your results back on the host needs to copy the data from the GPU, and then you can display it. That was the explanation about von Neumann machines. What can we do with von Neumann machines? But in a galaxy far, far away, someone thought about something else. And that's called data flow architecture. Data flow architecture is saying, let's not have all these registers, let's not have memory. We will do things differently. We will look at the program as if it's a graph. And the data that is flowing through the graph called tokens. And those tokens are basically meeting nodes, computation nodes, that will be computed, and the data is available when the token is available to the node. So that can make it a little bit non-deterministic because each time data can flow a little bit differently. It can take more time, less time. But in the end of the day, if we look at a simple program, you can see that the data flow is using A plus B, and then it's moving it to A3 with the multiplication. The same token is flowing to 2 different places, sometimes to 3 or 4. In the end, we are having Y and X from this graph, from the data flow itself. Pros, it's natively parallel. You can run it because it has no data hazards, almost no data hazards. You can run as many threads as you want on it because each thread will do something else and it will have its own tokens. So you're not interfering with each other. And it reduces data hazard heavily. Cons, how do you implement functions? How do you implement loops? Recursion? Memory? I don't know. Interrupts and exceptions? You cannot do that. Debugging? Horrible. Programming? No one tried. So what can we do? We can create something that's called hybrid data flow. Hybrid data flow is basically saying, we will be a data flow CPU, but we will be in one Neumann CPU as well. Let's do it together. And that's where MFC architecture comes in. That's what we are doing at Speedata.io. MFC performs very complex operation like we saw in CISC. Sometimes even more complex, but we are the same as RISC because we are encoding it to the same size. All the instructions are of the same size of 64-bit. We are handling large amount of data in the same time. We have vector instructions. We are using threads. Sometimes I will call them flows because it's data flow. It's not just a thread. And we will support divergence between those flows. Basically what it means, unlike in GPUs, if one thread goes to another direction and it does something else, we will not wait for it. We are not using swarms. How does MFC programming work? So each basic block of the program is a DFG. Basic block is something that is compiled. When the compiler is finishing up, basic block is something that it has only instructions without branches or fences. So each time that you have an instruction that is a branch or a fence, you are splitting the blocks up. That's what the compiler does for you. It is splitting those blocks. Each block that is a basic block, it has no branches or nothing, we are calling it a DFG. That's a diagonal flow graph. At the end of each DFG, there's a jump. We will always want to go from a DFG to another DFG to continue the program. All flows start from DFG number 1, and program ends when all flows meet together at a terminator DFG. This is an illustration of how your program might look. So we all threads or flows will start with DFG 1. Then you have a branch to DFG 3 or DFG 2. DFG 3 is a loop branch, a self loop. You have other branching to other DFGs. In the end of the day, when all flows are down to terminate, the program will terminate itself and will return the result. How do we do it? So MFC uses something that's called CGRA. Basically, CGRA is a mesh of computation nodes. Nodes are connected to static switches. Every node has its own operation. Tokens corresponds to flows. That means each token is corresponding to a flow that uses it. Token pass through execution nodes and in term nodes. Term nodes determine the next DFG for each flow. We have 3 different state storages, LVC, more about it later, main memory, DRAM memory, and streaming buffer. Streaming buffer is a very, very fast on-chip memory. That's how CGRA looks. You have the DFG memory or the DFG cache. It's connected to this CGRA, and each time that a CGRA is loaded into this, each time the DFG is loaded into the CGRA, it's computed to that DFG. So basically, you can see here those nodes. Each one of these nodes has its own ability. For example, we have ALU nodes, we have LSU nodes, and they work together. Here you have an actual illustration of an actual CGRA that we are using. That's how it's connected. It's showing you all the graphs or the flows of data and controls that are actually working. Here's an example of a pretty much complex DFG because almost all the units are taken here. Let's talk about the memory subsystem. So we are using L1, which is hardware managed cached, and it's backed by L2 and main DRAM. We have LVCs. LVCs, you can think about those as registers, if we had those registers. But what it does is basically when you need to move data from one DFG to another, you need to pass it through LVCs. Those LVCs are stored in the fast memory, in the stream buffer, to make it much, much faster than saving it inside the main memory. The streaming buffer itself, it is used to communicate those LVCs, but it's used by other components of the system. They are writing to the fast memory, MFC reads from the fast memory, or MFC writes to the fast memory, and the other accelerators that I cannot mention are reading from there. System accesses, we have 48 LSU accesses at the same time. LSU is load store units. So we have many accesses to our subsystem at the same time. And we are allowing that. I'm really sorry for the bad quality of this picture. I couldn't find something better. But basically, that's how our memory is connected to each other. It's called Banyan. Banyan connection, it's basically when everything is connected to everything, and you can take data from each and every unit that you have. So now that we understand that we have a very complex architecture that is data flow with one Neumann, how do we code it? We have created a new language that is called DOGE, Data Flow Oriented Graph Execution. It's a low-level interface to the APU. It's very similar to CUDA, so it's user-friendly. Gives the user the ability to access the low-level instruction and device build-ins. And we are using Clang frontend and backend that we are developing by ourselves. This is an example of a kernel that you can write by yourself. If you would look at it, it looks like CUDA a little bit. We are work in progress, so I'm using something very, very evil here that's called macro, but it will be gone in the end of the day. What happens here is we are defining a kernel that is called EX1 single DFG that has only one parameter that it receives, dout0. It's an out parameter. Afterwards, we have something that's called getFlowID. GetFlowID is very, very similar to CUDA getTID. And it returns the flow ID, which is inside the graph right now. Afterwards, we're taking the dout0 inside the TID, multiplying the TID by 14 and adding 11. Toy example does nothing. But that's not enough. We need to execute that kernel. And here again, you can see that it's very, very similar to what happens in CUDA. We have to allocate the memory on the device itself. So we're allocating the memory on device. We need to allocate memory on the host. It will be copied to the device. We are initiating it, copying the memory to the device, launching the kernel again with evil macros. And here in this macro, the kernel launch says EX1 single DFG. We need to launch this kernel. One means we are running with one block. And block size, it means how many flows we want for each block. And dout itself, of course, is the memory that will be filled out inside the kernel that is running. After the kernel run is complete, We need to copy the memory back from the device to the host. Again, very similar to CUDA. And then we can print and do whatever we want with it. This is work in progress. So most of those things are initial, and we are planning to do it even simpler than that. This is the actual assembly that we are using. We are producing this assembly with our compiler, and this is a DFG that I was talking about. DFG has only regular instructions in it. For example, we have the get FID. This is special instructions for our CPUs. IMM is an instruction that says, take this immediate and convert it into a token. madd, this is a special instruction that says, take the register 0 and register 1, multiply them, and then add 11 to them. Add-s is add with shift. Again, as you can see, we have special and very large instruction. We want to do as many things in one instruction. And then we are doing, by the way, register 5 is calculating the offset inside this 0 and then writing to it with STPP any. Afterwards, we have thalt. Thalt means that's it, like return. And this is the actual CGRA that is computed from here. Here you can see something that is very special for us because we saw that the DFG is so small, and this is the only DFG that we need to load, we could replicate it. That means that we have 8 replicas of the same program on the same CGRA. And that means that we can run 8 different threads on the same cycle. That was a toy, very simple example. And writing parallel code is really hard. So if you have any experience with CUDA, you know that writing that's really hard. Writing for us, it's even harder because it's data flow, it's different. Implementing SQL cases is even harder because you need to think about how each and every database that we will use or we will be integrated with will implement those things. And sadly, SQL is not standard. So almost all the instructions are acting differently on each database. How can we help to the users? So basically we're saying our users will not have to write code by themselves. We have Spark plugin. Our users will continue using the Spark as they used it before. Spark is producing something that's called plan. This plan is going to something that we call Pigeon, where Pigeon is our query compiler. The query compiler will use, I like to call it a very aggressive usage of metaprogramming for SQL algorithms. It will generate this code, then it will send it to our compiler, and our compiler will produce APU DFGs that will run on the APU and will return seamlessly to Spark. So the user doesn't write anything new, he doesn't need to learn anything new, doesn't need to learn a new database, just use Spark. Let's look at this example. We have a table that's called TBL. It's made out of 2 columns. One column is the ID column, the second column is the planet column. And as you can see, we have nulls here, or nones, and we have nones on planets as well. This is an SQL query, a very simple one that says, please filter out everything that has Mars in it. This is the plan that is created for this SQL query. A very simple SQL query is translated to this. You can see that even something that looks very, very small and simple will produce something that is really large, and you need to take into account all of these branches and execute them correctly. This plan is then goes through Pigeon, and this is an example of a code that is actually created. So here we have kernel that was created by Pigeon. As you can see, it's mostly readable. It uses a lot of metaprogramming everywhere. And we do add comments about what we are doing here for users to be more familiar or to read when they are reading the generated code. It will be easier for them. So here, for example, you have schema type. Schema is basically, it says, how is our table look like? The schema is constructed from int64 type and FLBA type, where FLBA type means bounded string. We're saying that we saw that in this case, there are no strings that are larger than 7 bits or seven characters. Then we are using row format. It's just something for rows, how we display rows in memory. Tile buffer is just how Spark works with us. Afterwards, we are saying we need to create a literal that will be used afterwards. Here you can see this code is a little bit older because we are still using C++17 in this case. In C++20, we will fix that to use non-template types because we can push strings now down the line, and it will be much simpler to read. Afterwards, we are creating another row format. Then we are saying, okay, please give me a column value. Column value, that means go to the row and take the column that is numbered by 1. Number 1 is planet. We are writing that as well. Afterwards, we want to create MFC equals type. That means we are creating an operator, the operator equals, that will work on the MFC column value that we just created, and MFC literal. It will see if the thing that is inside the column value equals to literal. Afterwards, we need to create a little bit more things. For example, we are taking planet again because we need to create another type. Now we want to check if it's not null. As you've seen in the table itself, you saw that we are used nulls. So if it's a null, we cannot do anything with it, and we need to see it's not null before we start checking it with literals. And as you see again, comments explain everything. Afterwards, we are creating another operator that does logical AND with MFC not null type 14, because we want to check that it's not null, and then we are saying and MFC equals type 16. So it's not null, and it equals to Mars. Afterwards, we are creating the filter operator. Filter operator takes the row and the logical AND type, and it will filter out the table from that. Afterwards, we are creating the row buffer type, the output buffer type. We are creating the output buffer schema, how it will look. Here we are starting creating something that's called processes. Processes are combining the operators together. So now we are saying that we want filter row process that will use the filter operator and the next processor. The next processor will be given to it after it will be called. We will see it in a minute. Then we are creating row scan. Row scan, it means let's read all the rows one by one from the table. And afterwards, finally, we can generate the kernel itself. So here you see composition. Composition is combining all processes together. We are creating this composition, and it's actually telling you what it's going to do. It's going to do a row scan. Let's scan all the rows. Let's filter all the rows where Mars is where we see Mars, and then we will do row sync. So basically, it says row scan. The next operator that it will be the filter row processor type 4, and then row sync will receive the data from those two things. Then we are generating the kernel that does the row scan filter process and the row sync. As you can see, all of our kernels will look very similar to this one, because all they need to do is just create the composite type, pass the correct parameters to the composite type, get the flow ID from it, run it in a loop for a stride size. Stride size, that means each thread will get a couple of rows to work on. Each flow will get a couple of rows to work on. And then just go to the composition and say process. That's it. When you say process, all the magic happens. All those templates that we saw before begin to be decomposed and used. So we are peeling all those layers of templates away, and executing each one of those one after another. That was a very, very simple kernel, a very simple example. Pigeon can scale out to queries that are much more complex than this one. For example, let's look at this query. This is more complex than what we saw before. We have select here, we have inner join, which is a very complex operation. We're saying the join should be on 2 different tables. We're saying that we have a where here. Where means that we will be filtering as well with an and. And in the end of the day, we have a group by. So a lot of things happen here. And I must say, this query is not complex as well, but it's complex enough for this talk. And Pigeon creates kernels for that as well. You can see that this kernel, kernel 0, looks very similar to what you saw before. Still, creating composition, taking the arguments, starting the process. And as always, we have the data that says what we are doing inside here. So we are doing row scan, filter row processor, projection row processor, has join sync processor. Afterwards, we need to create another kernel that does row scan from the new table that was written from kernel 0. We are filtering it. Then we are doing projection on it, which is something that it's basically projecting and creating a new table. Then we are doing hash join pipe processor on the new table. Afterwards, we are projecting it again. And then we are using group by operator. So we are taking all that we've done here, peeling all those layers, and creating a new table that is grouped by something that was asked there. And again, here we have another kernel. As you can see, all the kernels inside the kernel, everything looks almost the same, because everything that we do is done from the composition. So when you create those compositions, step by step, layers by layers, all the kernels are simple. And in the end of the day, what is left here is to do a group by row scan. That means go to the special table that you created for group by, do a projection from it, and then do a row sync. Row sync, that means take everything that you've done and write it to the table and return it to the user. That's it. Thank you. Any questions? Yes.
I'm trying to understand the bigger picture.
Can you come to the microphone, please?
So I'm trying to understand the bigger picture. Like, are you basically, if we want to use your hardware, you basically rip out the entire query engine of the existing database and you implement a new Pigeon, new variant of Pigeon? Or?
No, we are not creating a new variant of Pigeon. We are doing something that is very generic. We already have it for Spark, as I said. We didn't rip anything from Spark. As I mentioned, our users will still continue using the same Spark. We were just providing a plugin for them. They will use our plugin. It will be seamless to them. We will take the plan that was created by Spark. We will add more data to it that will be useful for us. Then we will take it to Pigeon. Pigeon will create that code. We'll compile it, send it to the APU, and then the APU will return it back to Spark. So nothing is ripped out. On the other hand, we're working on Presto as well right now. So it will be the same process, just with Presto.
Thanks.
So I don't do any database programming. I think this is very new to me, but I've done some GPU programming, and one thing that's very common there is you run out of memory bottlenecks. So I see that you're accelerating the CPU or the compute portion of this, but can you elaborate on sort of what the balance is typically in queries that you see for how much your memory bottlenecked versus how much your compute bottlenecked, and where you start to see advantages from accelerating compute to arguably free if you have dedicated ASICs?
That's a really good question. So we're accelerating analytics, and analytics is doing a lot of computation. We have a lot of cases that we already saw that they are doing so much computation, and even GPUs cannot help them because the data is structured. As I mentioned, when the data is structured, you need to do very bad things with GPUs, and you will not get the same results. For our cases, computation is the bottleneck for the users, and we're accelerating that. I/O, inside the chip, we are much faster than the other processors as well, but we are bounded by the network that will be used, and we are bounded by the host that will be used as well. I didn't mention that, but we will be a PCIe card inside the server. So we will still need the host to do work for us. We will still use Spark that is used on host. But to answer your question again, yes, we're accelerating analytics, and yes, we're accelerating by x60 at least.
Gotcha. And then maybe I can ask one more question. Can you elaborate on the decision to do CISC instead of RISC and why the...
We didn't do CISC. We did hybrid of everything. So it's RISC. All the instructions are in the same size, but we are doing more things in the same instruction. They will be encoded to the same size, nothing will change, but our instruction, what we are trying to do is because, for example, mul-ed, m-ed, or ed-s, those are two instructions in one, those are two things in one instruction, and we can do it in one cycle instead of 2 cycles. So we are trying to push as much as we can to the CPU to make it very complex to get the most out of it.
Gotcha. Thank you.
You're welcome.
Hi.
Hey.
Thank you for the talk. Quick question. Do you have any benchmarks comparing traditional way of doing things versus the new thing, the new approach, either real data or maybe simulated?
Only real data. We have a lot of benchmarks. You will need to sign an NDA.
Okay.
Is this a new chip or is this an overlay on an FPGA that's like commodity?
This is an ASIC. We already have an FPGA where we are using 2 of our accelerators burn on 2 different FPGA that are communicating with each other. But this is just for our use cases. Everything will be on an ASIC. All the accelerators and MFC, as I described it, will be on the same chip, will communicate with each other, and basically we need to be on tape out by next year. So the chip is coming. Anyone else? Thank you.